Howdy students, this is chapter 13, lesson 3. The objectives of this video will be to describe the effect of the external changes on the behavior of a system at equilibrium. And specifically, the four factors will include concentration changes, temperature changes, pressure changes, and what happens if we add a catalyst. So the response to this type of change in an equilibrium system is called LeChatelier's principle. LeChatelier's principle lets us know which way equilibrium will shift according to some sort of stress that is applied to the system. So we're going to be either shifting to the left, which is towards reactants, or to the right, which would be towards the products. We're going to cover four changes that can happen to a system that is at equilibrium already. The first, if you're keeping notes, this would be 1 out of 4. Changes in concentration. An increase in concentration is going to cause equilibrium to shift to the right to form more products. An increase in concentration of a product will cause the equilibrium to shift left towards the reactants. A decrease in concentration of a product will cause equilibrium to shift to the right to form more products, and a decrease in the concentration of reactants will cause equilibrium to shift to form more reactants. We call this the bathtub analogy. And what happens if we have a bathtub, and let's say we split that bathtub in half. If I've got water in that bathtub, and let's say that I add more water to the product side, the right side, what's going to happen to the water level in the bath? Well, if we add more water to this side of the tub will have to equilibrate and form more reactants on the left side. On the other hand, if we add more concentration, more water to the left side of the bathtub, we will shift the water level to the right to reestablish equilibrium. The same thing can be said if we create holes on either side. So if we create a hole, we scoop out water on the left side, equilibrium will have to shift to the left to compensate for the water level. If we decrease the concentration of the products, equilibrium will have to shift right to compensate for the decrease. So here's an example, not in your notes, but let's go ahead and look at this reaction. If we increase the concentration of carbon monoxide gas, then we're actually going to be consuming and decreasing the amount of H2 gas, because if we're shifting to the right and forming more products, H2 is not being replenished, so it will decrease in concentration. What's important to note is here, the equilibrium expression will not change, products over reactants. The value of K will not change. Another example, if we increase the product, well, in this case, both of these will increase on the reactant side because equilibrium will have to shift to the left. Again, equilibrium remains constant with a change in concentration. If we continually remove product from a reaction, we can actually force more of another product to be produced, or the same one that's being removed. So metabolic reactions is a good example of this. If we continuously remove ethyl acetate from our reaction vessel, it's going to allow us to continue to produce more ethyl acetate. If ethyl acetate builds up, it will slow the production of ethyl acetate. So let's run through a few examples for this. Reaction on the left, A plus B yields C plus D. If we add A or B, we are going to be increasing the amount of this to reestablish equilibrium. We will have to shift equilibrium to the right. If we remove A or B, we will create a hole on the left side, and we will have to be forced to shift equilibrium to the left. Okay, let's focus on C and D. What if we add C or D? Well, we're going to have to shift equilibrium to the left. Remove C or D, we're going to have to shift it to the right, just the opposite. Next example, we have the Fritz-Haber reaction, addition of N2, that is going to force equilibrium to the right. I would note that in this reaction, the concentration of H2 will be decreased. Addition of NH3, well, that will force equilibrium to the left. Addition of H2 to the right, I would note here that the concentration of N2 would be decreasing. Removal of NH3, that will create a hole on the right. We will have to shift to the right to fill in that hole. Okay, let's continue on with changes in temperature. This is change 2 out of 4 in LeChatelier's principle. Changes in temperature can be treated as changes in concentration if you know where heat is placed. So we have two trains of thought. We have exothermic reactions and we have endothermic reactions. Exothermic would be noted as a delta H value of negative. Heat is released. Endo, delta H value is going to be positive, and we will have an absorbance. Heat is absorbed. So what else? If this is the case, when we change temperature, we actually affect the K values. So if we heat up an exothermic reaction, K is going to decrease. If we heat up an endothermic, K will increase. Okay. One other thing to note is that in an exothermic reaction, we treat heat as a product. Endothermic, we treat heat as a reactant. If we can do this, then we can treat this just like concentration in the slide before. So here's an example. N2 plus O2 yields 2NO. Delta H is a positive value, so this is endothermic. Because this is the case, what I like to do is add heat or energy to the reactant side. We're going to treat it like a reactant here. So if I add heat, essentially what I'm doing is increasing the amount of this reactant. I'm adding heat to the left side. Equilibrium will have to shift to the right. If I decrease the temperature, then I will create a hole as a reactant, and it will have to shift to the left. Equilibrium, that is. Next example, down at the bottom, you'll see that delta H is a negative value, which means I can treat energy or heat as a product. If I increase the temperature, I will be adding energy to the right side, which will shift equilibrium to the left. If I remove that heat, I will be decreasing the energy as a product, causing equilibrium to shift to the right, excuse me. 3 out of 4, this will be changes in pressure. And as you know, pressures will only affect, you might want to circle this, the gaseous products and or reactants in the equation. Solids and liquids are already not included, but this would also exclude aqueous systems. If we increase the pressure of a gas, it will cause equilibrium to shift to the side with fewer gas particles. To summarize, increase pressure, we will shift to the side with fewer particles of gas. Decreasing the pressure will go the opposite, the side with more gas. It'll have room to spread out. If the system has the same number of moles of gas on each side, then we put no change in C. There's nowhere to shift if the gas moles are the same on left side and right side. Adding an inert gas will not affect equilibrium since the partial pressures of the gases will not be affected. Changing pressure will not have the value of will not affect the value of the equilibrium constant. So far the only thing we've seen that will change the equilibrium constant is the temperature. Let's look at some examples. Increasing the container volume. Well, if I increase the container volume, that would cause pressure to decrease. We have to be careful here. On the left side of the reaction, I have 6 moles of gas, and I have 4 moles of liquid on the right and 1 mole of solid. So I have 0 moles of gas on the right side. So if I decrease the pressure, we're going to go to the side that has more gas particles, which would be to the left. If I decrease container volume, that would cause an increase in pressure, which would go to the side with fewer particles, which would be to the right. Argon, along with other examples like helium, neon, argon, krypton, what else? Nitrogen gas. These are all inert and will not change the shifting of equilibrium. Next example. In this reaction, I have 2 total moles of gas. We're going to use the coefficients here. Didn't mention that, but there's a 1 here and a 1 here. That gives for 2. And we have 1 mole of gas here on the right side. If we decrease the container volume, we will increase the pressure, and we'll go to the side with fewer particles. That should shift equilibrium to the right. Helium gas is inert, so there will be no change. And let's go ahead and do the last one down here. We have 4 moles of gas, 3 and 1. On the right side, we have also 4 moles of gas. So whatever the change for pressure, it will not affect the shifting of equilibrium. And 4 out of 4 would be the addition of a catalyst. In the last unit, kinetics, we learned that a catalyst that is added to a vessel will change the pathway that a reaction takes to form products, oftentimes lowering what we call the EA, the activation energy. Now, in equilibrium, we have a forward reaction and we have a reverse reaction. We have a K for the forward reaction and a K for the the reverse reaction. And I'm talking about the rate law, K, lowercase. The forward reaction is going to equal the reverse reaction rate. As far as changing the value of equilibrium, though, it will have no effect. So we throw this in here to let you know not to be fooled when they say that we have added a catalyst. It will not change the value of equilibrium. Let's do some mixed problems and we will finish notes here. Consider the reaction, which is exothermic. Right away, I know that energy will be a product. A vessel contains these 3 gases at equilibrium. Predict how each of the following stresses will affect the concentration of O2. So here we're specifically trying to isolate what's happening to O2 and also the value of K. NO2 is added. NO2 is a reactant. If we increase the concentration of NO2, equilibrium will shift to the right, which forms more oxygen gas. So let's fill this in. We're going to increase the concentration of O2, and there will be no change for the value of K. If N2 is removed, we're decreasing the concentration of N2. Then we will create a hole on the product side, which will force equilibrium to the right, which means O2 is increased, and there will still be no change on the value of equilibrium once it's reestablished. The volume is halved. Well, if we half the volume, or decreasing the volume, we're going to increase the pressure. So this is a pressure problem. If I look at the moles of gas, I've got 2 moles on the left side and 3 moles on the right. Increasing pressure will shift to the side with fewer particles, so this should shift to the left, which would have an effect of a decrease in the concentration of O2. There will be no change in the value of the equilibrium constant. D, helium is an inert gas, and right away I know that there will be no change, which means no change in O2, no change in equilibrium. E, temperature is increased. Well, remember, energy was a product because it is an exothermic reaction. So if I increase the temperature, I'm adding product, which will force equilibrium to the left. This would decrease the concentration of O2. And temperature, what's going to happen to the value of K? I'm going to flip back real quick, see if we can find that. Let's see. If we are increasing the temperature of an exothermic reaction, K will decrease. Okay. So K is going to be decreased. A catalyst is added, no change for equilibrium. That would speed up the forward reaction and speed up the reverse reaction as well.